All right, guys. So we're doing a rerun of the DeepSeek paper. So as you guys know, about a week or two ago, this new AI model out of China basically took the world by storm, called DeepSeek R1, which is sort of the reasoning alternative to the ChatGPT o1, which I guess is now o3. So basically want to do a deep dive into the paper, just to get an understanding of how it works. And, you know, we as a community can get a chance to, explore what's in the paper and possibly discuss ideas from that paper and maybe how we can add our own contributions to the field, given what we'll learn in the paper. So we have Jordan Madden. He's gonna basically take us through the paper. He's currently doing his PhD in AI. So he's gonna walk us through the DeepSeek paper. And so over to you, Jordan.
All right, thank you. I'm just trying to share my screen. Can you set it so that I can share my screen too?
Yeah, you're good to.
All right. All right, let me know when you can see it. Wait, is my screen being shared? All right, hold on. Let me try it again.
Yeah, we're seeing it.
Okay, cool. So yeah, like Matthew said, we're going through the DeepSeek R1 paper, and at a very high level, the purpose of this paper is to just demonstrate how DeepSeek used a technique called reinforcement learning to figure out how to get LLMs to do a kind of quote unquote reasoning natively instead of having to be prompted to do it. So yeah, the purpose of this paper, as it says right here, is to introduce the first generation models, first generation reasoning models, DeepSeek R10 and DeepSeek R1. So R10 is a model trained by large-scale reinforcement learning without any supervised fine-tuning. And so they say that it demonstrates remarkable reasoning capabilities. However, it encounters challenges such as poor readability and language mixing. So to address those issues and to enhance the reasoning performance, they introduced DeepSeek R1, which incorporates like a multi-stage training and cold start data before reinforcement learning. So DeepSeek R1 achieves performance that is comparable to OpenAI O1 on reasoning tasks. And to support the research community, they said that they open sourced DeepSeek R10, DeepSeek R1, and 6 dense models distilled from DeepSeek R1 based on the Quen and the Llama models. So just a note before we really get into the paper, throughout the paper, when they're talking about OpenAI O1, you'll often see it followed by 4 numbers. So in the 4 numbers, the first 2 numbers represent the month, second 2 numbers represent the day. So this version of OpenAI O1 was released on December 17th. Throughout the paper, you'll see another version of OpenAI O1 that was released in February. So it's going to start with 09. All right. So getting started with the paper. So this paragraph right here, well, these 2 paragraphs really are a very high level summary of the paper. So they said that they take a first step towards improving language models' reasoning capabilities using pure reinforcement learning. And their goal is to explore the potential of LLMs to develop reasoning capabilities without any supervised data. So to do this, they use DeepSeek V3 base as their base model. So DeepSeek V3 base as the base model, and employ an algorithm called GRPO, which stands for Group Relative Policy Optimization, as the reinforcement learning framework to improve model performance in reasoning. So they said that R10 exhibits superhuman performance. Well, not superhuman, but super performance on reasoning benchmarks. And they gave some examples of the scores that it achieved. Yeah, so here is the other OpenAI model that they use in the paper. So this was released on September 12th. So 09/12, September 12th. Right, so the model that was released on December 17th, the 12/17, would most likely be more powerful because it was released later and it was trained. It had additional training and probably safety work done to it. So that model would probably be a bit more powerful than the OpenAI 01/9/12. All right, but so they say that DeepSeek R1 encounters challenges such as poor readability and language mixing. And to address that, they introduced DeepSeek R1. So what DeepSeek R1 does differently is it incorporates a small amount of cold start data and a multi-stage training procedure. And in addition to the reinforcement learning that's done in R10. So to do that, they collect thousands of cold start data to fine-tune the base model, the DeepSeek V3 base model. And after that, they perform reinforcement learning similarly, well, exactly as in DeepSeek R10. So the rest of the paper, well, yeah. And before we get into the rest of the paper, rather, they also say that they explore distillation from DeepSeek R1 to small dense models. So I would say that these two paragraphs here are like the core technical contributions in terms of novelty. And then this paragraph talks about the distillation that they do to base models to demonstrate that base models can be made into reasoning models. Well, not even base models, but, well, yeah, base models, because they do say base model. But yeah, they say that small models can be made into reasoning models by distillation from a big, powerful reasoning model like R1. So yeah, the rest of the paper is essentially going to walk you through how they did all of that. So yeah, their contributions are post-training, which is the reinforcement learning procedure that we talked about to develop R10 and R1, as well as distillation, which is what we just talked about in this paragraph. So here's where they start talking about R10, section 2.2. So they say that in this section, they explore the potential of LLMs to develop reasoning capabilities without any supervised data. And the algorithm that they use is Group Relative Policy Optimization, or GRPO. So traditionally in reinforcement learning, you would have some agent A that takes some action. And this action is in an environment E, right? Then the environment would send both the state of the environment after the action is taken and a reward to the agent. So the reward tells the agent how good its action was. So for example, if you're trying to train a self-driving car, right, you'd want it to stay on the road. So every time the agent turns the wheel, if the car stays on the road, it would get a positive reward. And if it comes off of the road, it would get a negative reward. And so the aim of reinforcement learning is to take actions that maximize the reward that you get. So it's essentially it's learning by trial and error. So that's like a standard reinforcement learning pipeline. But in the context of LLMs, you'd have some LLM that would generate some text. Let's call that text T, right? And the environment, there isn't a standard environment as in the normal case of reinforcement learning. The environment, I guess, is us, but it needs some reward. So it needs to get some reward so that it knows if the text that it generated is good or not. So it would have some reward function R that tells the LLM how good the text that it generated was. And so this reward function is described by this. Well, actually, let me rephrase that. So in LLM, well, in the context of LLMs, you're trying to maximize the reward that you get from the reward function. And so the GRPO algorithm formulates that trial and error process in terms of this objective function. So what the objective function does is we're trying to maximize this objective function. What objective function does is it takes the ratio of the current, the LLM versus an old LLM, and you don't want LLM updates. You don't want the updates to the LLM to be very large, because reinforcement learning with large updates becomes very unstable. So to make the learning process very stable, you want to make sure that the ratio between the old and the new, the old and the updated model is somewhat small. And to make sure that you can keep the model constrained within some, to make sure that you can keep the updates constrained within some area, you take the minimum of this division and this clipping function, right? So what this clipping function does is if this ratio is too large, it will clip the magnitude of the, how do I describe it? It'll clip the magnitude of the update to within some small parameter epsilon from the originals, right? And then, so that ratio is multiplied by an advantage function A, right? And so what that advantage function does is it tells you how good each generation from the LLM was relative to every other generation in the sample. So what would happen is that the LLM would generate probably multiple samples. So if you ask the LLM a question during training, say, what is 2 plus 2, right? And it generates 4 outputs, for example, right? So one output 1 would say 4. Output 2 would say the answer is 4. Output 3 would probably say 5. Output 4 would probably say 100, right? So there are 2 answers that are correct. So this one and this one, and these 2 are very clearly incorrect, right? So you would get some reward based on the correctness. So the algorithm, you see, it gives you a reward for each of these generations. So R1, you'd get some positive reward, let's call it 1. R2, you'd get a positive reward, let's call it 2. So for R3, because it's incorrect, you can either get a negative reward or no reward. and R4, you can get the same thing. Let's give it a negative reward instead. Right. So what this advantage function does is it says for each of these responses, wait, this is 1 as well. You get a reward of 1. So what this advantage function says is that for each response, for each of these individual responses, it takes the mean of all of the rewards and subtracts it from the individual reward and divides it by the standard deviation. So it normalizes each individual reward with respect to all of the other rewards. So A1, for example, 1 would be 1 because R1 is 1 minus the mean, which is 0, and then divided by the standard deviation, which let's call it 2, right? So A1 is equal to a half. A2 is the same thing. It's also equal to a half. A3 is going to be equal to A4, which is going to be minus 1 minus 0 divided by 2, which is equal to negative 1, right? So the advantage here would be positive when the reward is correct, and it would be negative when the answer is incorrect, basically. For each of these, when you have a correct answer, that's going to boost the reward. That's going to boost the objective function that we're trying to maximize. And if you have an incorrect answer, it's going to minimize that. And so we're training the model via reinforcement learning, via trial and error, to get rid of behaviors that produce negative rewards and negative advantages, and only focus on answers that give you positive rewards and positive advantages, so that you can maximize this overall function. And then there's this second term here called the KL divergence, which essentially just measures how close the outputs of the model are to the output of a reference. And you want to make that as small as possible. So you want the output of the model to be as close as possible to the output of the reference. So that's what this term here does. All right. So
looking back at that, I just realized something. The reference,
Mhm.
did people say what that reference policy is?
Yeah, I didn't see it. I looked around for it, but I didn't see it mention what the reference policy is. I couldn't find anything.
Yeah. I just realized that, yeah, that part, that piece wasn't mentioned.
Yeah.
It's
So
reference policy that they're thinking, yeah.
so I wasn't sure if they had like a separate model that they were trying to make it sound like,
Yeah.
or I mean, maybe they should use the what do you call it?
Oh,
The D3 model, because they were trying to
Mhm.
get its text to sound like similar to that style or something. But I don't know. It didn't stay concerned.
Yeah, I think I remember them mentioning something about them using outputs from the previous iteration or something like that.
Mhm.
I don't know if maybe it's a earlier version or as you say, maybe a V3 or something like the base model.
Yeah.
Mhm.
Yeah. So I mean, I'm really not too sure, but yeah, they didn't specify. It didn't. Well, I didn't see where they specified what the reference model is. So that was kind of confusing to me. But
Niall has a question.
oh yeah.
Chat.
What's up? Quick question.
I can go ahead, yes, sir.
Yeah,
Yeah.
man.
Yeah, man. Cool. I just want to verify something, Sir Madden. I realized like so you're doing a comparison of like I guess a robotic agent or otherwise agent versus the LLM and the application or reinforcement learning here. I just wanted to
Mhm.
know so I know pi here represents a policy. And usually a policy, like when you're thinking about a robot, for example, you think about a sequence of actions. To be clear,
Mhm.
in the context of large language models, we're thinking about the sequence of words that it spits out when we talk about a policy.
Yeah, I'd say that's the equivalent. I'd say that mm, yeah, I'd say that's the equivalent. I mean, I'm not an expert in reinforcement learning by any means, so I could be wrong when I'm saying this, but I think that the policy refers to the LLM itself because that's what we're trying to optimize.
Okay,
So like the outputs of the LLM. So yeah, it would be the text that comes out, I'm assuming.
all right, thanks.
Yeah, more
Yeah.
than likely because for each output, well, typically for reinforcement learning, you have a set of actions and the policy is more or less um the distribution of those actions based on the current state. So in a way, in a sense, for the LLM, it would be more or less the distribution of words in terms of which word it chooses based on the prompt or whatever in this
Yeah,
case.
most likely.
All right, thanks for that clarity.
Yeah. I mean, yeah, if you have questions in the future, you can just interrupt me. You don't have to like say that you have a question. You can just interrupt me and I'll stop.
All right, thanks.
But yeah, so so this is the crux of how the GRPO works. And so it's trying to maximize this objective function here. So the obvious question is like, how does it calculate the rewards that it uses in the advantage function, right? So that's what this next section talks about. So they say that to train R10, they adopt a rule-based reward system that consists of two types of rewards, an accuracy reward and a format reward. So the accuracy reward would tell you if the answer is correct or not. And then the format reward would tell you if the answer adheres to the format that the LLM should generate. So the accuracy reward is pretty obvious. It was similar to the example that I gave, where if the answer is correct, it would give you a positive reward. And if the answer is incorrect, it would either give you a 0 or a negative reward to discourage that kind of behavior. But the format reward is a bit trickier. So in the format reward, they say that they want the model to put its thinking process between the think and the closed think tags. So that's where table 1 comes in here. So this gives you the template for a DeepSeek R10 prompt, right? So the system prompt to DeepSeek R1 says that this is a conversation between a user and an assistant. The user asks a question and the assistant solves it. So the assistant first thinks about the reasoning process in mind and then provides the user with an answer. The reasoning process and answer are enclosed within the think and the closed think tags, and then the answer and the closed answer tags, respectively. So the format reward would give the model a positive reward if it puts its reasoning process between these tags, and then it puts its final answer to give to the user between these tags, right? So if it's thinking about, let's say the 2 plus 2, they could say, oh, well, we know that 1 plus 1 is equal to 2, and 1 plus 1 plus 1 plus 1 is equal to 4, and 1 plus 1 is equal to 2, then 1 plus 1 is equal to 2, then 2 plus 2 is equal to 4, or something like that. That was a really contrived example, but that might be like how a reasoning trace might look for it, right? And so that would be your reasoning process. So that reasoning process would have to come between this think and this closed think tag. And then with that, given that, so since it's come to the final answer, it would spit out its final answer in between these tags. And the final answer is what you would see as the user. So the final answer would be, oh, the answer is 4, or 4, just 4. Right. So those are the format rewards to encourage the model to separate its reasoning process from its final answer. And they do that so that for UI purposes mostly, I think, so that like if you go on the chat.deepseek.com website and you use the reasoning model, you'll notice that its reasoning traces are gray, but then its final answer is like bold. So it knows, the UI knows what's the reasoning separately from what's the answer because of this format that it has to stick to, right? Yeah. Right. And so, yeah. So they say that.
Guys, before we continue, I don't know if you guys have been using the LLMs, but I do realize that DeepSeek's reasoning trace seems to be a lot more long, well, a lot longer and more detailed than the others. At least the ones I've used. So that seems to help.
Yeah, definitely. I agree.
More about it down in the paper in terms of inference time versus, or the length of reasoning versus the accuracy. Like if you give it more time to reason, then it should more or less get a better response.
Yeah. So one of the important things that the DeepSeek paper says is right here, that they don't apply a neural reward model when they're developing R10, because they find that neural reward models may suffer from reward hacking in the reinforcement learning process, and it just complicates the whole training pipeline. So what they mean is, like in a standard algorithm, like PPO, proximal policy optimization, that's used for reinforcement learning. In the case of LLMs, they train a reward model to give them the rewards, and they estimate the advantages. They use a technique called advantage estimation to get the advantages. Well, general advantage estimation, I think it's called. But here, they use a lot simpler rewards here, and they have an actual heuristic, well, not a heuristic, but they have like an actual formula to generate the advantages. So that cuts down a lot of the development complexity and in the reinforcement learning process, and just makes things a lot more efficient in terms of the speed of the development, or the speed that the researchers can move in, because they don't have to collect data to train a reinforcement learning, a neural reward model or anything like that. They just use these verifiable type rewards, where there are settings where the answer is either correct or it's not, and you can verify that it's correct. All right. Yeah. So then, to train R10, they design a template that guides the base model to stick to the specific instructions. And so in table 1, as we talked about up here, the template has to produce a reasoning process followed by the final answer. And then they say that they intentionally limit the output of the model to that format, to ensure that they can accurately observe the model's progression during the reinforcement learning process. Right. And so these are some metrics of R10 as it was being trained. So it's being compared to OpenAI's O1 mini and O1 from September. And you can see that it's better than O1 mini at this benchmark with one pass, and with 64, it's better than both O1 and O1 mini. In the Math 500 benchmark, it's the best model there. In the GPQA, it's better than O1 mini, but it's not as good as O1. And here, it's not as good as either of them. And here, it has a lower rating. But like you can see that it achieves competitive performance to O1 models on average, because some of them it's higher than it's better than O1, some of them it's worse, but on average it's competitive. And you can see that as the model was trained, so as there were more and more training steps done, so this is probably, yeah, so as more and more training steps were done, right, the accuracy of the model on the AIM benchmark was just steadily increasing on average for R1. And so this is the OpenAI O1 model with 64 steps, and this is the O1 model with a single step. And so you can see that when R1, like as R1 is being trained, it eventually becomes better than the O1 models on that benchmark. Yeah. And yeah, one other thing that they say is that the performance of DeepSeek R10 can be augmented through the application of majority voting. So what that does is, well, what I think they're saying is they basically generate multiple outputs, and then the most common output is what they take to be the final answer. So if you ask it, what is 2 + 2? And then they have like 10 outputs. If 8 of them say 4 and 2 of them say 5, then they'll take 4 as the final answer. So I think that way they get more reliability in the response process. And as well, another interesting thing that they noted was that while they were training the model, it learned to talk itself through the problems more and more. So you can see that as the training was going on, the length of the response kept increasing approximately linearly, right? And so the reasoning that they're talking about here in this paper is where the model walks itself through the problem and thinks through the problem before coming to a final answer. So as the training was going on, they found that the model was doing that more and more frequently, essentially. So it was generating more and more text in the final answer before it outputted it. So that's just going to show that the reinforcement learning actually was working to improve the reasoning capabilities of the model. Now, one interesting thing that they say here in the paper is that they found an aha moment in R10. So the aha moment is basically where the occurrence of an aha moment. They say that this moment, as illustrated in table 3, which is here, occurs in an intermediate version of the model. So during this phase, R10 learns to allocate more thinking time to a problem by reevaluating its initial approach. So if you look here, this is an example of the question that R10 was asked during its training. Well, just part of the question. right? So it's a math question that has an answer, right? And so this, everything below the line is the model's response, right? So it starts by talking about, oh, okay, so to solve the equation, let's start by squaring both sides and yada, yada, yada. But then in the middle of it, trying to solve the problem, it says to itself, oh, wait, there's an aha moment I can flag there. Let's reevaluate this step by step to identify if this correct sum can be blah, blah, blah. So they realize that the model realized that it made a mistake during its reasoning, and then it stops itself and it starts the reasoning process over. And they found that pretty interesting because they said that it underscores the power and beauty of reinforcement learning, because rather than explicitly teaching the model how to solve a problem, they simply provide it with the right incentives, and it autonomously develops advanced problem solving strategies. Right. So although the R10 was really impressive technically, they did encounter some drawbacks, as we talked about earlier in the introduction. So although it exhibits strong reasoning capabilities and it autonomously develops powerful reasoning behaviors, it faces several issues. For example, it struggles with poor readability and language mixing. So poor readability means that it's a struggle for humans to read the output of the LLM, to read its reasoning process. And language mixing means that its reasoning process might start in English and then go to Japanese and then go to German and then switch back to English before going to Spanish. So there are multiple languages in the reasoning process that wouldn't make sense to a human reading it. So to make the process more readable and to distribute the models, they developed DeepSeek R1, which is a method that utilizes reinforcement learning, human-friendly cold start data, right? So DeepSeek R1, section 2.3 dives into how they did that, right? So they said that they had two questions after they developed R10, right? So the questions that they had were, can reasoning performance be improved, or can the convergence of the process be accelerated by incorporating a small amount of high quality data, like cold start? And then the next question that they had was, how can we train a user-friendly model that not only produces clear and coherent general capabilities, right? So basically on that second question, they had that question because of the poor readability and the language mixing of the R10. And so DeepSeek R1 is their set of experiments to try and correct that. Right. So how do they do that? All right. So they start, to do that, they design a pipeline to train R1, and the pipeline consists of 4 stages. So this is stage 1, the cold start. So unlike R10, to prevent the early instability in the reinforcement learning training, they constructed a small amount of long chain of thought data to fine-tune the model as the initial reinforcement learning actor. So what they mean there is that they collected some data and then they would do some supervised fine-tuning with that data on the model, so that the model kind of is fine-tuned to do some reasoning in a sense. So how did they collect the data? So they said that they use few-shot prompting with a long chain of thought as an example, and then they had a model generate that. Or they directly prompted models to generate directed answers with reflection and verification, or, well, and not or, they gather DeepSeek R10 outputs in a readable format. And finally, they refine their results through post-processing with human annotators. So they collected a couple thousand cold start data to fine-tune the DeepSeek V3 base as the starting point for reinforcement learning. And they said that compared to R10, the advantages of this cold start data is that it increases the readability and the potential. So they say that a limitation of R10 is that its content isn't suitable for reading because of the problems like language mixing. And they get into the language mixing thing specifically here. So it might mix multiple languages, or it would lack markdown formatting to highlight answers for users. So in contrast, when they're creating the cold start data for R1, they explicitly design a readable pattern that includes a summary at the end of each response, and it filters out responses that are not user-friendly, are not reader-friendly. So the output format of this cold start data is, so they would have the reasoning process within some special token, and then the summary after the reasoning process. And then, yeah, and then with regard to the potential, they say that they designed the pattern for the cold start data with human priors, and they observe better performance against R10. So because of the improvements in the results that they were getting here, as opposed to just the direct reinforcement learning, they say that they believe that the iterative training that they're doing with R1 is a better way for reasoning models, as opposed to the straight reinforcement learning that was done for R10. All right. Now, so after they collect the cold start data and fine tune the DeepSeek V3 base, then they do what they call reasoning-oriented reinforcement learning. So this is step 2 of the process. So in this step, they apply the same large-scale reinforcement learning training that was employed in R10. So everything that we talked about up here with the GRPO and the reward modeling and the training template and all of that, they repeat the exact same thing here as the second step in the reinforcement learning process. Now, they said that to mitigate the issue of language mixing, they introduced a consistency reward, an additional consistency reward during the reinforcement learning training, which is calculated as the proportion of target language words in the chain of thought. So, for example, if the model generates 100 words, if 60% of them are in English and 40% are in Spanish, then the reward would be 0.6, for example. But then if 90% are in English and then 10% are in Spanish, then the reward would be 0.9 if we wanted to generate English. So essentially, the portion of our response that is in the target language is the reward. And what's interesting here is that they said that experiments show that such alignment results in a slight degradation in model performance. However, the reward aligns with human preferences, making it more readable. So they were okay with there being some decrease in performance because they wanted the output to be human understandable. So in the third stage of the R1 development, of the third stage of the R1 pipeline, they use rejection sampling and supervised fine-tuning. So when the stage 2 process is complete, they use the model that is generated there to collect supervised fine-tuning data for the next round. And they say that unlike the initial cold start data, which primarily focuses on reasoning, This stage incorporates data from other domains to enhance the model's capabilities in stuff like writing, role-playing, and other general purpose tasks. Specifically, they generate the data and fine-tune the model as described below. So for reasoning data, they curate reasoning prompts by performing rejection sampling from the checkpoint from the above reinforcement learning training. So if I understand it correctly, rejection sampling is essentially just generating multiple outputs. And then if the output is incorrect or not what you want, you just discard it. And then the ones that are correct or the ones that are what you want, you keep it. So, yeah, they said that in this stage in this data generation stage, they expand the data set by incorporating additional data. And they said that because the model's output is sometimes chaotic and difficult to read, they filtered out some of the reasoning processes that had things like multiple languages, overlay long paragraphs, and code blocks. So they generated this data to have multiple responses that are correct. And in total, they collected about 600,000 reasoning-related training samples, right? And then here, they also collected non-reasoning data to make the model more general purpose, so that you could use it you could ask it in theory stuff like to help you write your essay, or to help you review your homework or something like that. So for the non-reasoning data, they use such as writing, question answering, self-cognition, and translation. They adopt the DeepSeek V3 pipeline and reuse portions of their supervised fine-tuning data set that they developed in DeepSeek V3. And so they said that in total, they had about 200 examples that are unrelated to reasoning. So they fine-tune the V3 base for 2 epochs using the above curated data set of about 800,000 samples. Now, stage 4 in the process is to do like a more general reinforcement learning. So they said that to further align the model with human preferences, they did a secondary reinforcement learning stage aimed to improve the model's helpfulness and harmlessness while improving its reasoning capabilities. So they said they trained the model.
Where it says non-reason, so it says it fine-tunes the DeepSeek base on this data set. So had they already done the initial learning on the base?
I think so.
I
think so. I think that the base would have been the model that they would have gotten here.
Because this after fine-tuning the base on the cold start data, we apply reinforcement learning.
Yeah, so I think that the model that they're talking about here is the output of step 2. Although I'm not 100% sure because they did say DeepSeek V3 base, but it doesn't make sense to me that it would be a 4-stage pipeline if you're throwing away the first 2 stages to restart from the base. Or maybe I'm misunderstanding it, and maybe they're using the model that they generated in step 2 maybe they're using the model that they generated in step 2 to generate this 600,000 reasoning-related training samples.
We curate reasoning prompts and generate reasoning by performing rejection from the checkpoint. Yeah, so basically after they train the RL, the base with the RL,
Yeah.
They
So
use that
yeah, so my
checkpoint
second
to
thing was
collect
right.
data. Mhm.
Yeah, so it looks like my second thing was right. So basically this in stage 2, this reasoning reinforcement learning. So up to that point, this is just R10 with some cold start data, right? And then they use this um, model, the R10 with the cold start data, to help generate the 600,000 reasoning related samples.
Mhm.
And then add it to the 200,000 training samples from the DeepSeek V3 dataset, and then use that dataset to train. So
fine-tune
they
DeepSeek
use that
base.
dataset to fine-tune the base model. Yeah.
Oh.
So
Is
it's like a roundabout process, it looks like.
is that they
So
use RL to train the base, then use that to get data, and then use that to train by the base, to fine-tune by the base.
yeah. It's kind of strange, but I mean it works. So maybe people will figure out that they don't need all of those stages. Maybe they could just generate the 600,000 training samples with something else, and then do a next stage of reinforcement learning on R10 to get it to work better. But anyways, so after they fine tune the V3 base on the 800,000 samples, they go to step 4 of the process, which is a broader reinforcement learning. So this is a secondary reinforcement learning stage, aimed to improve the model's helpfulness and harmlessness while improving its reasoning capabilities. So, so for the helpfulness, they found that for the helpfulness, basically, if you remember earlier, there in R1, they had the model's reasoning process, and then they had a summary of the reasoning process. So for the helpfulness, they said that they focus exclusively on the summary, ensuring that the assessment emphasizes the utility and relevance to the user while minimizing interference with the underlying reasoning process. While for harmlessness, they evaluated the entire response of the model. So not just the summary, which included the reasoning process, to identify and mitigate any biases, risks, or harmful content that might arise during the process. And ultimately, the integration of reward signals enables them to train a model that excels in reasoning while prioritizing helpfulness and harmlessness. So in this secondary reinforcement learning stage, I assume that they also use the GRPO, but they don't say that explicitly. They say that they train the model using a combination of reward signals and diverse prompt distributions. And then for reasoning data,
methodology outlined
in
R10.
So
so
they use the GRPO.
Okay.
So they use the GRPO to do the reinforcement learning for the reasoning data. And then they say that for the general data, they resort to reward models that capture human preferences in complex and nuanced scenarios. So it seems like the reasoning data, they use the GRPO, and then for the general data, they use another algorithm that has a reward model. Well, I'm not sure if they mean a neural reward model or the reward model that they had above. But since they made the differentiation, I think that they mean a neural reward model.
Yeah, which they probably trained or some supervised, because they capture human preferences in complex. So yeah, they probably just trained some reward model on human data. Yeah.
Okay. But yeah, so after that, if you remember, So the first contribution that the paper made was in post-training, which is the reinforcement learning process to develop R1 and R10. So we just finished talking about that. Now, the next contribution that they made was on distillation, which is empowering smaller models with the same reasoning capability. So they say that to equip the smaller models with the reasoning capabilities, they directly fine-tuned open source models like Quen and Llama using the 800,000 sample data curated with R1. And they find that the straightforward distillation method significantly enhances the reasoning ability of smaller models. They use an assortment of Quen models and some Llama models to do this. So they say that they only do supervised fine-tuning and don't include reinforcement learning, even though reinforcement learning could possibly boost the model performance. So that's an open research direction that they're leaving on the floor, like to see if people can do reinforcement learning to further boost the model performance. But yeah, like just a side note, like I think that the terminology that people are using in machine learning nowadays is so confusing because distillation, like here they say that they're talking about distillation, but they're really just doing some fine tuning on the data set that they had. So like when like distillation typically means training. Well, I mean, I guess it is the same thing, but like distillation typically means like training directly from the outputs of another model instead of from like a data set that a model generated. So I mean, in that sense, I guess it's the same thing, like since you're fine-tuning from the outputs of another model. But
so wait, this 800 is the same 800K them use to
yeah, this
train R1?
yeah, this same 800K.
That's weird.
So
Wait,
basically, they use this 800K samples, and they
yeah.
curated it with R1, and then they just use that data to do fine tuning of these
Oh, so
small models.
R1 curated using the 800 samples curated with R1. Huh.
Yeah.
Curated with R1.
Mm-hmm. So it doesn't really say how it did that.
Curated R1. Okay.
Well, yeah. So yeah, they say that they only do supervised fine tuning and no reinforcement learning in this distillation process. So yeah, I mean, I don't know. I guess because they're training on the outputs of another model, like it's technically distillation. But
the 800K, how did it get it again? 200K came from
DeepSeek V3, and yeah, so 200K came from 200,000 came from DeepSeek V3. Like they say that they called V3 to generate chain of thought before answering the question by prompting.
So okay, so all these came from okay. So all of these came from the initial training, the initial cold start with the RL. The 600K, it seems.
Yeah, it came from the third stage of the R1 pipeline.
Yeah, so in a sense, yeah, because it would have been come from that model, it would have come from that checkpoint when they had initially done the reinforcement learning after the cold start. So they collected 600K reasoning thing there from that, plus the 200K non-reasoning from V3. So yeah, I mean both come from models. So in a sense.
Yeah, I just think that like in machine learning, well, in computer science generally, like there are a lot of really loaded words, and I think distillation is becoming one of those words, like kernel, for example. Like it's just one of those words that you use, but you don't know exactly what it means. Like, because like you say kernel, what do you think of Linux kernel or CUDA kernel or something like that? Like if you use kernel arbitrarily, like you don't know exactly what it means. And I think distillation is becoming one of those words. But that's besides the point. So yeah, going on to section 3. This is where they do their experiments. So
Well, I
they
guess
use.
my thing is this: if distillation seems to just be fine-tuning on good data, wouldn't you just keep using the model to produce that data and just get the data? Like if, for example, if I were to get high quality data without using a model to get that data and I do the same fine-tuning, would that still be distillation?
Mm.
I guess that's kind of what you're saying. Like um, yeah, like what it coming from the other model, why does that make it more? Why not just use data? I guess the model creating the data that take out the work of. And I guess if the model performs better than humans, then you could say that it's making more high quality data. So I don't know.
Yeah. But yeah, that was just like a tangent with a thought that I had. But yeah, anyways, so in the benchmarks, they say that they evaluate the model on a couple different benchmarks. So they use the MMLU and a couple versions of it. They use CEval, if eval, frames, GPQA, simple QA, SweBench, and a couple others down here. And they talk about the prompts that they use for the evaluation. They said that they evaluated them using prompts from the simple evals framework when they were evaluating standard benchmarks like MMLU and GPQA and drop. So for MMLU Redux, they use the zero eval prompt format in a zero shot setting. And then in terms of MMLU Pro, since the original prompts are few shots, they decided to slightly modify the prompt to the zero shot setting. They said that for code and math benchmarks, they use the human eval. Well, they said the human eval dataset covers 8 mainstream programming languages. And the model performance on live code bench is evaluated using chain of thought format with data collected between August 2024 and January 2025. Yeah. And then for baselines, they conducted a lot of evaluations against DeepSeek v3, Claude Sonnet, GPT-4o, OpenAI o1 Mini, and OpenAI o1 from December. And they used the Claude 3.5 Sonnet from, where's this, October, I think, the 10th month. Yeah. And they said that accessing the OpenAI o1 API is challenging in China. So they report its performance based on official reports. So basically what they did was they went to probably like the OpenAI website where they, in their press release for o1, where they released the numbers that they got for these evals, and then they put those numbers to their paper, basically.
Yes, they said that it was difficult to access the API. It's still from multiple reportings. It seems like they use GPT outputs help train.
Yeah, so that's kind of interesting. Yeah, so for evaluation, the maximum generation length, they set it to 32,768 tokens. And they found that using greedy decoding to evaluate long output reasoning models resulted in higher repetition rates and variability across checkpoints. So what they defaulted to was the pass at K evaluation, and they reported the pass at 1 using a non-zero temperature. So they used the sampling temperature of 0.6 and a top p-value of 0.95 to generate K responses, where K is typically between 4 and 64, depending on the size of the test set. So the pass at 1 is calculated with this formula. Where PI denotes the correctness of the ith response. And they say that this method provides reliable performance estimates. And then for AIM 2024, they also report the consensus or the majority voting results using 64 samples, denoted as cons 64.
Okay. So basically they're saying instead of just picking the one that it gave the highest finger to, it made it generate like a certain amount of responses. And I guess it's what's that P? What's PI? Oh, the correctness.
Yeah.
So yeah, they evaluate the correctness of each of those responses, and it's like average out the to find what the actual. So instead of just in the first one, it make it generate like 64 or so responses, and then average out the thing there, the evaluations on that.
Yeah, exactly.
Mm-hmm.
Yeah. So these are some of their evaluation results. So like they said, they compared it to Cloud 3.5 Sonnet 4.0, DeepSeek V3, which are all standard like assistant type models. They compared it to O1 Mini and O1 from December, which are reasoning type models. So which is why they have this separation here, and then their model is here. So they have data that is, they have English data, English eval benchmarks, code benchmarks, math benchmarks, and Chinese benchmarks. So there are a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So there's a total of 21 evals. And they said that R1 achieved the best performance on 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 out of the 21. And so OpenAI 01 achieved the best performance on, what's this, 5? 5 of the benchmarks. Cloud 3.5 Sonnet achieved the best performance on 2 of them, and DeepSeek V3 on 1 of them. Am I missing anything? I don't think so.
Which ones did it? I guess, let's see. The ones that OpenAI beat it at are what? MMLU, Pass 1, GPQA, MPQA.
Simple QA, Code Forces.
So it seemed O1 is better at, well, according to this coding, or according to this benchmark. But it does beat it on live code bench.
Yeah.
Look, Claude have the highest in SWE. Math, well, it beat it, outperformed it on all the math evaluations. Yeah.
Yeah. Yeah. So, the results were pretty impressive compared to the other big well-known models. And for the distilled models, in their evaluations, so the distilled models are all down here, while the big assistant models like GPT-4o, Claude 3.5, and O1 Mini, and QWQ, which is a Quen's reasoning model, they say that their distilled models beat the other models on 1, 2, 3, 4, 5 out of the 6 categories, with O1 Mini beating the distilled model only on the code forces. Only on the code forces benchmark.
That's very impressive because
These
I
models
mean,
are
look at the
small.
parameter size versus some like 4.0 or O1 Mini, which probably like hundreds of billions of parameters.
Yeah, definitely.
Yeah, that's pretty impressive.
Definitely. And so, yeah, they're saying that simply distilling R1's outputs enables the R1 7B, which is the Quen 7B, to outperform non-reasoning models like 4.0 across the board. So they say that this model across the board outperforms 4.0, which it does in everything except this and this.
It
Yeah.
seems like distillation is the way to go because, I mean, anybody right now can literally just take some responses from one of the, using DeepSeek or OpenAI, just use the API or whatever. Find a small model like a 1B model or whatever, and just, fine tune that, which probably shouldn't even take much money to do, really.
Yeah.
And you have a model that's outperforming
These
some of the
big,
top models. Like,
yeah, definitely.
you spend way less money. So you just make the big players spend all of the money, and you just use their work to produce something better with a lot cheaper. I think that's
Yeah.
probably where you're going to see a lot of smaller players that taking that avenue instead, are trying to create these big frontier models. It's just not,
Sustainable.
yeah, it's just not worth it now. I think investors are probably even seeing that, like, yeah, the play right now is these distilled models.
Yeah, I agree. So, in section 4, they have a discussion where they start talking about distillation versus reinforcement learning. So, in section 3, they found that by distilling R1, small models can achieve impressive results. But they wanted to figure out if the model could achieve comparable performance through the reinforcement learning without any distillation being done. So what I wanted to know is if they do reinforcement learning on the base models instead of the fine tuning, can they achieve comparable performance? So they did some large scale reinforcement learning on the Quen32B base using math, code, and STEM data for 10,000 steps, resulting in R10 Quen. So, yeah, so it's interesting that when they did the same, instead of doing the fine tuning, when they did the reinforcement learning, the results of the distilled model are better across the board than the model where they use the reinforcement learning. So for small models, it's probably more effective to distill from a big model than to do your own training of the model from scratch. And they noted that here, where they said distilling more powerful models into smaller ones yields excellent results. Whereas the small models relying on the large-scale RL require enormous computational. The second thing that they found was that while distillation strategies are economical and effective, advancing beyond the boundary of intelligence may require more powerful base models and larger scale reinforcement learning. So I thought it was interesting that they said that because thus far, the only learning paradigm that has consistently outperformed a human baseline has been reinforcement learning, like in things like AlphaGo and games like Atari and those kinds of things. So
I think what this is saying is basically the reinforcement learning can work, but it needs a good base to start with. So trying to do reinforcement learning on this small, 32B model, straight like that, without any cold start, just straight RL.
Yeah,
it's not gonna get the performance like how you get with just a distill, because it don't have a good base that it's starting with, basically.
Yeah, and I mean, I think because it's pretty clear that because of R1 and R10, that reinforcement learning does work. So I agree with you there that it needs a good base model. Yeah. And then one thing that I like about this paper is that they talk about the stuff that they tried that didn't work. So they said that they tried using a process reward model, which is a method that guides the model towards better approaches for solving reasoning tasks. But they found that it had three main limitations. So they found that firstly, it was hard to explicitly define a fine-grained step in general reasoning. Secondly, they found that determining whether the current intermediate step is correct is hard. And finally, they found that once the process reward model is introduced, it inevitably leads to reward hacking. And retraining the reward model needs additional training resources and complicates, so it needs additional training resources and it complicates the whole design. So they said that while it demonstrates a good ability to re-rank the top end responses generated by the model or assist in guided search, its advantages are limited compared to the additional computational overhead it introduces. Then the next thing that they tried was Monte Carlo tree search. So this was what was done in AlphaGo and AlphaZero, which is where AIs were used to beat humans at Go. And so they tried to enhance the test time scalability. And so what they did was they broke down the answers into smaller parts to allow the model to explore the solution space systematically. So they prompted the model to generate multiple tags that corresponded to specific reasoning steps for search. So how they trained it was, well, during training, they used the collected prompts to find answers via MCTS, guided by a pre-trained value model. And then they used the resulting question answer pairs to train both the actor model and the value model, iteratively refining the process. But they found they had a couple challenges doing this. So they said that unlike games like chess and Go, where the search space is well defined, they said that token generation has an exponentially larger search space. So they tried to set a maximum extension limit for each node, but that led to the model getting stuck in a local optima, which you don't want during training. And secondly, the value model directly influences the quality of the generation since it guides each step of the search process. Now, training a fine-grained value model is inherently difficult. and that makes it difficult for the model to iteratively improve. So they said that while AlphaGo's success relied on training a value model to progressively enhance its performance, that principle proved difficult to replicate in our setup. So they said that while MCTS can improve performance during inference, when paired with a pre-trained value model, iteratively boosting the model performance through self-search remains a significant challenge. So it's an open area for research. Finally, they
Where you continue, I find that interesting because, well, from the rumors I'm hearing that all three actually involved, well, they managed to get search to work with it somehow, which is probably what pushes it over the others right now. So I do imagine that the frontier models will be looking into that, or trying to get that work. So, I mean, it's obvious from the paper they were trying to get it to work, but maybe they just couldn't get it to work. So maybe OpenAI figured out some way to scale it properly. I mean, they probably have more resources so they can fool around with that more.
Yeah.
But yeah, I get what I'm saying about the value model, because with AlphaGo, what they used to train the value model is just supervised learning. They'd have the image of the game board and the move sorry, not the move, whether the game would have been lost or won from that state essentially. But with token generation, there's so much different. It's hard to tell whether it's gonna whatever it's doing is right or wrong at whatever step it is at.
Yeah.
It's a lot more difficult because it's harder to get data on that basically.
Yeah. Yeah. So yeah, so in the in the conclusion, they were just wrapping up basically, reiterating what they did. They developed R10, they developed R1, and they explored distillation to extend the reasoning capability to small models. Now, they had a section for future work where they say that they plan to invest research into a couple directions for R1. So they want to improve the general capabilities of R1 because they say that the capabilities of R1 fall short of V3 in tasks like function calling, multi-turn things, complex role-playing, and JSON output. So they want to figure out how long chain of thought can be leveraged to enhance those tasks. Now, they also say that R1 is currently optimized for Chinese and English, which can result in language mixing. So R1, so they said that they want to address this limitation in future updates. They also say that they want to work on prompt engineering. So they said they noticed that it's sensitive to prompts, and few-shot prompting consistently degrades its performance. So they recommend that users describe the problem and specify the output format using a zero-shot setting for optimal results. Now they want to work on that to improve that. They want to improve its capabilities in software engineering tasks as well. And because they said that due to the long evaluation times, which impact efficiency of reinforcement learning, large-scale RL hasn't been applied extensively to software engineering. So DeepSeek R1 hasn't demonstrated a huge improvement over V3. So they want to address this in future versions by implementing rejection sampling on software engineering data, or by incorporating asynchronous evaluations during the reinforcement learning process to improve efficiency. Yeah, and that is the end of the paper. The rest of it is just the references that they had and the names of the contributors to the project. Yeah, so does anybody have any questions about anything in the paper?
Yeah, I mean, I'm sure there's some in terms of the actual training process, some finer details they didn't, because when I was watching an interview that Lex Friedman did, some guys on there was basically kind of going into the possible process that they use. It seemed they definitely did a lot of low-level optimization on the GPU side. So apparently they went even lower than CUDA
Yeah.
to optimize the GPUs they had available to them. So it definitely seems they have a good engineering team over there, for sure.
Definitely.
Yeah.
Definitely. I saw that they did that too. It was really ridiculous that they like bypassed CUDA and were using like, well, I mean, they had to get the best performance out of the GPUs, but it's ridiculous.
I think in terms of the AI for the field, the good of the field, I think this was a bigger moment, the whole DeepSeek moment was a bigger moment than the ChatGPT moment. Reason being, I think it's going to lead to a higher, basically an exponential runoff, like in terms of explosion of the work that's gonna be coming out. 'Cause I mean, every day now I'm hearing about somebody training a $50 version or $100 version. Like, yeah, people are making cheaper and cheaper versions of these things that people spent billions of dollars on so far. So yeah, I think it's definitely, to me, especially because it's open source, done more for the field than what GPT
Yeah.
would. So I'm excited to see what the future holds in terms of open source development. I think eventually, just like how Linux open source and it's installed on every server in the world. Android, same thing. Yeah, I think the same thing is gonna happen with AI. Eventually, open source is gonna win out.
Yeah.
You know.
Yeah, most likely. I think so too.
Yeah. Yeah, I think it's better for the field, to be honest, than just having one corporation decide. If AGI is achieved in our lifetimes, it's better if it's open to the broader community. So at least everybody has some way of monitoring it versus it just being in the hands of a few tech billionaires, essentially. It's like the future of humanity. So yeah, I'm all for it, really.
Yeah.
Yeah. All right. Well, that brings us to the end of our paper discussion. We'll be having more sessions like these in the coming weeks, so stay tuned. We'll be looking at all the papers in the field, having more engaging discussions. So see you guys next week.
All right.
All right. Bye, guys.
Bye.